All right. Hey, thanks. Thank you so much for the organizers for making this great workshop and for giving Argoverse an opportunity to show off what we've been up to. And hey, everybody. I'm James. I'm a principal scientist at Argo and a professor at Georgia Tech. I'm going to be giving a brief intro here, and then you'll hear from Ben, Joni, and Will talking about the various competitions that we've recently hosted. But before we talk about the competitions, I want to say a brief word about the Argoverse 2 data set. So 1 year ago to this day, actually, it was when we gave the first teaser that we would be releasing more data sets, these Argoverse 2 data sets, the 4 data sets that you see here. And when this March, we were able to publicly release them. And I'll just give a very brief overview of what these are because we're using some of these for the competition. So the sensor data set is really inspired by influential data sets like Waymo Open Dataset and New Scenes. We wanted to make a bigger sensor data set with more objects and more challenging scenarios, LiDAR, 3D annotations with track ID, so it's also a tracking data set. And it's sampled from 6 cities. For example, this is Palo Alto. One differentiator with this sensor data set is that we have a relatively large taxonomy of objects. So here there's 30 object categories listed on the x-axis, and on the y-axis is their frequency and log scale. And compared to our first sensor data set or to other data sets, we have a bigger taxonomy, I would say. And for a lot of these classes, we have enough examples, even for classes like articulated bus or stroller, that we can train and evaluate models on them. So 26 of these categories we evaluate on. So in the object detection competition, you will see we are reporting their average performance on all of these categories. And some of them are obviously quite difficult. Another differentiator is that the annotations and the evaluation for this sensor data set are relatively long range. So here's a histogram. On the x-axis is range, and on the y-axis is the number of annotations. And especially in this 100 to 150 meter range, we have more annotations than, again, these other data sets that have been great and influential and inspired us. So in this competition, you'll see that we'll be evaluating methods out to 150 meters, which is important for safe self-driving. And that's really challenging to recognize all these objects at long range. So one way to maybe make that easier is that we also released this large LiDAR data set. One of the first large, unlabeled data sets of self-driving data that's intended for things like self-supervised or semi-supervised learning. So maybe you can make a better object detector by training 20,000 scenarios that are actually longer in duration than the sensor data set scenarios. But they're unlabeled except for the fact that they do have HD maps under them. The third data set I'll highlight is a new motion forecasting data set. And again, Waymo released a new motion forecasting data set, and this sort of inspired us to up our game as well. And it is more challenging than the original Argoverse motion forecasting data set. We have more interactions with the AV. We have denser environments. Here you can see pedestrians and vehicles. And we are asking you to forecast not just what vehicles will do, but also what bicyclists, or in this case, pedestrian, will do. And when Will presents, you'll see how the different methods do for this. This is this distribution of where the motion forecasting data set is sampled from. So this data set and all the others I'm talking about come from 6 cities. The motion forecasting one is the most scenarios, so it's sort of the easiest to make a visualization of. But you can see that they come from wide areas of Pittsburgh, Miami, and the other cities that Argo operates in. And it's a similar distribution for all the data sets. And then one more differentiator from Argoverse 1 is that we have a longer forecasting horizon. So we're asking you to predict what's going to happen 6 seconds in the future instead of just 3. To make it a little easier, maybe you also get a longer history. You get to observe 5 seconds before you make that future prediction. And then the final data set I'll highlight is a map change data set, which we believe is the first of its kind. So what we're seeing here on the left is sensor imagery, the front camera in this case. And on the middle column is some rendering of our HD maps. For this task, you need to train machine learning methods that say, does this sensor data set and does this map match? And as far as we know, this is the first data set where we have lots of examples of an autonomous vehicle actually encountering map changes in the real world for the first time, coming up to an environment that it might have driven 100 times before, but this time there's a new crosswalk, or there's a bike lane that was moved, or there's other dramatic construction. And the task is to be able to say that, hey, the HD map representation I have doesn't actually match the sensor data I'm seeing, which again, an important task for autonomous vehicles. Sorry, all of these data sets share the same HD map representation. Here's a visualization of a few scenarios. And it's richer than the Argoverse 1 map representation. You can see here crosswalks are visualized, actual lane geometry with lane boundary types like double yellow or dash white. And all of the data sets share the same API, so it's easy to connect data sets together. But visit argoverse.org for more details on all these data sets. They're now all public, as is the API. Today, we're going to drill down deeper on 3 competitions that we ran this spring. The first one is 3D object detection with this new Argoverse 2 sensor data set. Ben will present that in a moment. Then we'll talk about stereo depth estimation. This still uses actually the Argoverse 1 sensor data set to get that stereo data. And then finally, will talk about motion forecasting with the new Argoverse 2 data set. All right, I'm going to hand it over to Ben now.
Thank you, James, and thank you to the organizers of this workshop. So today I'm going to be presenting the Argoverse 3D Object Detection Challenge. And so first, one thing I want to point out is, why might you want to use this data set? What new thing do we offer? Now I want to share this video highlighting the detection range that we use for evaluation. So what you're seeing a bird's eye view. The ego vehicles in the center of the field of view. And you're seeing a 50-meter range, which has maybe been traditionally sort of a range that might be used for 3D object detection. You see in AV1, we had a 100-meter detection range, but now we're extending AV2 to 150 meters. And so we think that this will help researchers really showcase their methods that focus on long-range detection, because this is a difficult and important problem that needs to be solved. So additionally, we have this large taxonomy that James mentioned. We have 30 classes, 26 of which we have enough instances to evaluate. And we have instances of dog, right? You can see someone the dog on the sidewalk, right? And additionally, you see this, you see school buses labeled with stop signs, actually. And if you back project the RGB, you can see this rich texture on the objects and use that to further enhance your algorithms. And that's not all. There's many more. Like I said, there's 30 different categories, but we use 26 in the competition. And you can imagine that some of these, especially the small, rarer objects such as animal, etc., they're pretty difficult, and especially at range. So how do we evaluate our methods? So we take a lot from new scenes and how we designed our metrics. They're fairly similar. We have average precision, which you all, I'm sure, are very familiar with. And we additionally have our true positive metrics to help measure different forms of error. So we have translation error, scaling error, orientation error, but these are all used in conjunction for the final ranking metric, which we call CDS. So this is similar to the new scene score, but the difference is that we're weighting it against MAP. So the thought is that your detector, if it does not perform well and get a high score in MAP, you will be penalized. So that is sort of the key difference here in how we rank our metrics. And so this encapsulates scaling, the orientation of the different objects, etc. So now I want to get into the winner of the competition. And this was from Jin Feng et al. From Baidu Research, University of Macau, Beijing Institute of Technology, and the University of California, Irvine. Now, this is a really nice method, and it certainly really outperformed our baseline, and I'd like to tell you a little bit more about it. So their method, they do some kind of things that are quite often used for these sorts of methods. First, they aggregate the LiDAR frames from the past. They take the past 4 frames, put the ego motion, compensate them into the normal frame, the reference frame. And they incorporate HD maps as well as splitting by distance so that they can kind of utilize finer grained resolutions closer to the ego vehicle. And so we see a 1.5 increase in CDS and a 1.9% increase by doing this distance split. So they use the same architecture as we do for our baseline, which is center point. But like I said, they incorporate these multi-resolution blocks. And interestingly, they see a giant performance by changing their head split, as in like, they have all these different detection heads like we did too for the baseline, but they find that this configuration that's shown above has a 6.4% increase. And compared to, I mean, they admit in their report that, this was one of the biggest differentiating factors out of all the different sorts of, optimizations and methods that they added to boost performance. And then lastly, they have some test time augmentations, flipping the image, rotating, et cetera, to even further squeeze a little bit more performance. So as you can see here, this is CDS, and the left bar is our baseline, and the right bar is the detectors, the top submission. And you can see that they blow our baseline out of the water. They over double the performance in MCDS, which I thought was very impressive. And secondly, as I mentioned, the true positive metrics, we also see, keep in mind, lower is better in this case. And you can see they've made pretty meaningful improvements, especially in orientation error. So performance at range, this is another thing we wanted to look at because we have this 150-meter evaluation range. So how did these detectors do when we actually drill down and look at how they're doing in different bands of this this range? And so what you'll see right here is, they're already over doubling our performance again from 0 to 50 meters. They're more than doubling our performance at 50 to 100. And interestingly enough, they triple our performance at 100 and 150. Now, I must say that, these slides are meant to encourage, you all that have fantastic different methods that you can apply to this task, that there's still room, tons of room you can see to be gained in this space. And we would love to have, each and every one of you submit to this challenge. And last, here's a CDS breakdown. So you can see some pretty impressive performance increases. These are, they're ordered from top to bottom in terms of the highest diff between the performance. So you can see on school bus and construction barrel wheel device, you see these just absolutely massive increases. Bicycle construction cone. It's really impressive stuff because these are some tough categories, some of them being very small. So lastly, I just want to show some qualitative results before I pass it over to Joni to present the stereo competition. So on the left-hand side, you're seeing our baseline, and the right-hand side, you're seeing the winner. Now, one interesting thing that you can see is this also has the same, sorry about that. This is the same scene that has the person walking the dog. So if you watch carefully, the AV makes a turn, and then on the left-hand side, you'll see right there, there's a person walking their dog, and if you, it's a little bit hard to see, but I believe that the top performing method does have a better aligned bounding boxes on that particular category. So the rest of these are a little bit easier to see. Right here, if you look at the bus making a turn right there, you can see that the orientation from the baseline method is rather poor. And in general, you can see that the bounding boxes for the top performing method are much more stable from what I can see. Just a few more qualitative results. So right here, you can see lots of orientation error. You see those, we're about to pass those vehicles, and especially going into the turn, you can see a lot of, the detector's a bit confused as to what orientation the vehicles are facing. In this particular example, you can see if you take a look at that truck on the left-hand side, you can see that it just, the performance is a lot more stable on the right-hand top performing method. And lastly, I have one more video. If you take a look at the bus on the left-hand side, you can see that again, it's more well localized from the top performing method. So that is it for the detection competition. And now I will hand it off to Joni to talk about stereo.
All right. Hi, everyone. I'm Johnny, and I'm a research scientist at Argo. So I'm going to be presenting about the stereo depth estimation competition. So let's start with the data. So the Argoverse Stereo dataset is based on the Argoverse-1 3D tracking dataset, and it has over 6,000 high-resolution stereo image pairs. So that's about 16 times bigger than the Kitty stereo dataset. That's the dataset that we got inspired by. And the ground truth from that we created was generated from the LiDAR accumulation using scene flow, a scene flow method. So we don't rely on any semantic information or CAD models. So it's basically using the point cloud as input to generate this accumulation, LiDAR densification. So the LiDAR range is up to 200 meters. That is about 2 times the range of the sensor used in the Kitty dataset. And we have a bunch of diverse driving scenarios for the dataset. So here's a plot showing the number of arrays or the number of ground truth information available in this dataset by the depth or the range. So the blue area here is the Argoverse Stereo dataset. The green is the Kitty dataset. And we can see here that we have way more ground truth information than Kitty. That's about 16 times bigger or more frames than Kitty, and a longer range as well. So here are 2 examples. On the left, we have the ground truth depth overlaid with the stereo image. And on the right, we have the depth for the foreground objects only, because we've released these masks where you can have this information about only the objects of interest. So yeah, we ran this competition last year, and all methods achieved great accuracy, but they had poor inference time. So they were running within like seconds or even minutes to infer a single disparity map. So for example, the winners method inference time was in the orders of 1.8 seconds on an NVIDIA 1080 Ti. So they were pretty heavy models. And this year, we want to emphasize on real-time performance. So the algorithms must produce these depth estimates within 200 milliseconds or less on an NVIDIA Tesla V100 in order to be eligible for the prizes. And these values are self-reported by the competitors by using our benchmark scripts. So here are some challenge stats. We had 355 submissions from 11 participant teams, and we had 7 entries in the public leaderboard. So here's how we evaluate. We are basically using standard stereo metrics, the same metrics used in the Kitty leaderboard, which is this the percentile of disparate errors averaged over all the ground truth pixels, and the disparate errors average over only background or foreground regions that we call the all, BG, and Fiji. And the disparity error is basically the absolute error that is greater than a threshold, basically 3, 5, or 10 pixels, and a relative error greater than 10%. So here's a snippet of the leaderboard. We can see we have all these metrics. We are ordering the leaderboard by the all 10, which is the average over all the pixels on the image that we have the ground truth information. And here I'm showing the top 3 methods: the GM stereo, MSCLab, the LRM, and the 5th method is our ACVNet baseline. And what's new in this leaderboard is this last column where we have the inference time in milliseconds. So this plot is, I think, the most interesting plot for this competition that shows this the error by the latency in milliseconds. So here on the far right, I put these the winners method from last year's competition, which is this MSCLab, and you can see it takes about one second as a latency here on the Tesla V100 GPU. And all these new methods for this the newest competition are much better in terms of latency. So the GM stereo, for example, is 5.7 times faster than the MSCLab. And the LRM is even faster than that, but compromising a little bit with the accuracy, which is running about 150 milliseconds. And our baseline is a little bit is lower than that. And just to be clear here, not all methods could run their models on the hardware specified, that's the V100 GPU. So we basically use this tool, the deep learning GPU benchmark, to just get some scaling factors. So we could just calibrate all this latency and make sure the latency values were as if they were run on a V100 GPU. And the AV2 that's our baseline. That's going to be presented at CVPR. So please check this paper out. It's going to be presented on Thursday. That's a cool paper to check it out. So here is the percentile of disparate errors for all the methods. So we have these orange bars, which is for the errors for all the foreground, all the pixels. The green is for the foreground pixels, and this gray is for the background pixels. So you can see here that the GM stereo and the MSCLab, which is the winner from the last year, they share similar error, but GM stereo is doing a little bit better in the foreground regions. And our baseline is not doing that like a job in the foreground regions as well here. So let's announce the winner. So for the first place, that's going to be the GM stereo. And for the honorable mentions, we'll have the MSCLab and the LRM. So congratulations to all these teams. They did a pretty good job. So I'm going to give like a brief overview about the methods and what they've done. And the cool thing about these methods is that 2 of these methods will be presented at CVPR. So the first one, the winner, that's the GMS stereo, learning stereo disparity via global matching, will be presented on Wednesday. But the method that they will be presenting at CVPR will be the GM flow. And so they basically repurpose a little bit this method for the stereo case. And they are using transformers to enhance the extracted features using cross attention. And they are simply using some global matching formulation to get this dense correspondence by feature similarities. So the second method is the MSCLab, this deep equilibrium model for memory efficient stereo matching. That's another paper that we presented at CVPR, but that's not from the same authors. So they just got inspired by this method and just proposed this stereo method here. And they use this raft based model, which is a state-of-the-art model for the optical flow. And they use this deep equilibrium for memory efficiency. That's another paper that they just combine these 2 information. And another cool thing about this method is that they proposed a new synthetic data set that was built on Carla. And they used pretty much the Argoverse Stereo setup, the focal length, the height of the camera, and so on. So they just could synthesize an Argoverse Stereo data set. The last method is the LRM, which is based on the PWC for optical flow. Again, they just repurposed the method for the stereo case. And also, they proposed a new synthetic data set built on the Carla simulator. So they get this very dense stereo depth using the synthetic Argoverse stereo rig, which is the same camera height, the same baseline and focal length. And they had about 100,000 frames for this. And we have some examples here on the right with these synthesized images using Carla. So here's an overview about all these methods plus our baseline. In the first column, we can see that most methods in the deep stereo field, they're training on synthetic data. And the most widely used is the scene flow data set with flying chairs, flying things, and others. But the MSCLab and the LRM also use their Carla synthesized data based on the Argoverse Stereo setup. And then they fine-tune on the Argoverse Stereo data set. But the GM Stereo not only refine on the stereo data set, but also on the virtual kitty and the driving stereo. So they have a pretty large data set that they've collected. So they have this transformers-based model. So that's why they claim that they need more data for that to generalize well. The input shape is of high resolution for the Argoverse Stereo data set. For our baseline, we downsampled the imagery by a factor of 4, GM Stereo by a factor of 2, and the MSCLab and the LRM just use the full image. That's the simple trick that people use, just trade off the image resolution to get better latency, and you can just upsample your output depth map. And the cost volume, there are different strategies. So for example, the AV2 also have this 4D correlation volume, but they use some attention-based mechanism plus 3D convolution. That's quite expensive. But the GM Stereo use a transformer-based architecture to just enhance the features, and they just perform a global correlation, like just for every single pixel, just compute on the epipolar line what's the most similar one directly without any convolution. That's why it's quite fast, and it's pretty neat that they got this very competitive results. MSCLab is using a multi-scale correlation volume plus some refinement using the raft strategy. And the LRM just used the PWC multi-scale convolution, the correlation cost. So here is some extra results where we broke down the error by the range. And on the right side, you can see on the y-axis, you can see the number of rays or the number of depth information that you can see. So if you look at the gray bar plot behind the curves, that's basically the number of depth information that you have over range. So that's going to decrease over the depth, because the faraway objects, we don't have many lighter hits on those objects. So that's why the curve is just going down. And what's interesting is that if you look at the middle curve, it seems that all methods are performing pretty well until this 90 meters range, and then it starts to degrade. Basically, the curves are just like inverting because we have less information in this range. So that's why the error is kind of growing up. And for the background, since you have more information on the background, generally, the methods kind of stay more stabilized, let's say, in these areas. So here I'm going to show some visual results, but let's just break down this image. On the top row from left to right, we have the left stereo image, the ground truth overlaid on the image, and the top three lab, our baseline AV2, and the winners from last year competition, MSCLab. You can see this is like a very crowded scene, lots of objects, lots of cars, and all depth maps looks pretty smooth and piecewise continuous. That's beautiful. But it's sometimes not good to look only at the depth images. They might be misleading. You need to just try to reproject onto a point cloud and try to see the geometry of these depth maps. So that's what I'm going to show next here on these visualizations of the point cloud as a over-the-shoulder visualization here. So I have the ground truth on the top left, the GM Stereo, the winner, MSCLab, and our LRM, AV2, and the the winners from 21. So you can see here, I think it will have some pedestrian crossing the street. I'm not right. Yeah. So So let me show another depth map example. So here we'll have a pedestrian crossing the street. The car turning around. And then again, for the same scene, this point cloud representation with some normals to get some better geometrical information here from this. It's quite noisy because we haven't performed any sort of filtering on the sky pixels. We don't have any ground truth in the sky pixel. That's why it's kind of cluttered on the top region. Here again, and this is the last visualization that we have. This is a cool scene where we have this large truck just crossing by the street. A bunch of depth information from the surface. You can see that most depth maps looks quite nice. And here is the point cloud representation with some lighting effects. So yeah, that's the visualization, some takeaways. That's pretty cool that we are seeing, like, for example, from last year's competition, we've seen all these nice models that got pretty good results, but they were very heavy based on these very heavy cost correlation volumes. That's pretty expensive in terms of memory and latency. But now it seems that the community is kind of moving away a little bit to use this transformer-based cost volume, like the GM flow and GM stereo, so they can avoid some 3D computations on the volume. So for example, the first place, the winner here is 5 times faster, about 190 milliseconds than last year's winner, which was taking about 1 second with similar error. And most methods are just adapting the optical flow models, the PWC-Net, GM flow, the RAFT, they're all optical flow models, but you can imagine that stereo is just a special case. Instead of looking at the 2D region, you can just constrain your search to a polar line. And all these methods are also, not all, but the LRM in the other one is simply generate some Carla synthetic data for pre-training, and that seems to help with the generalization, so you can get a better statistics that match the test data set. So that's it for the stereo competition. Now I'm gonna just pass over to Will. Will represent the motion forecasting.
So hey everybody, I'm Will from Argo's prediction team, and next I'm going to discuss some of the results and insights from this year's motion forecasting challenge. So starting with a bit of history, it's been really cool to see how the research community has interacted with Argoverse over the last couple of years. In particular, the motion forecasting data set has seen quite a bit of community adoption, with more than 100 papers referencing or reporting results on that task alone. And even with the release of similar data sets in more recent times, it's really cool to see the enduring popularity of Argoverse as a benchmark for vehicle motion forecasting. And some of our top leaderboard entries, such as LaneGCN, VectorNet, TNT, to name just a few, have had significant influence on today's state of the art, which we'll discuss in a little bit. But first, we'd like to present the results from this year's motion forecasting challenge, which is now in its 4th iteration and features a brand new data set. And with over 6,000 leaderboard submissions from 400 participating teams, these challenges have been an exciting source of competition and innovation for the community. But before we go on, I'd like to briefly introduce the task of motion forecasting as set up in Argoverse. In our benchmark, snapshots of real-world driving have been recorded and captured as individual prediction scenarios, each featuring a focal agent. The goal is then to use the observed history of this focal agent, along with social and environmental scene context, to predict the future motion of this agent. And to capture multimodality, models are allowed and encouraged to generate multiple predictions, with the goal of generating a high probability trajectory that matches the ground truth future. So how do we measure if a set of predictions is good? In our challenges, we've used 3 primary metrics to capture forecast quality. The first is minimum final displacement error, or min-FDE, which is pretty simple. It's defined as the endpoint error of the closest forecasted trajectory. The second is miss rate, which is a binary score that captures whether the min-FDE was greater than 2 meters. So this is motivated by desire to reward accurate forecasts in difficult scenarios, since you can't optimize that metric by simply driving error down to 0 in the simplest settings. And the last metric we use is an augmented version of min-FDE that adds a Breyer score component. So this captures the probability associated with the best trajectory, ensuring that forecasts which are confidently accurate are rewarded more than scattershot predictions. So with the problem set up out of the way, let's dive into this year's Argoverse challenge. What's new here? The first big change is the use of a brand new motion forecasting data set, in this case, Argoverse 2. And with 250,000 brand new scenarios over 6 cities, this has allowed us to double the forecast horizon from 3 seconds to 6 seconds. We've also increased the size of our object taxonomy from just 1 class to 10, with forecasts being evaluated for 5 of them. And with so many changes to the data set itself, the one thing we did hold constant is the evaluation metric. So for this year's challenge, we continue to use Breyer min-FDE evaluated over the best 6 trajectories. Okay, so highlighting some stats from this year's challenge. Let's see. There we go. It was really cool to see Argoverse 2 get picked up by the community so quickly. And despite the 5-week time frame, we saw more than 800 submissions come in from more than 30 teams. So that's a great turnout, and there's lots of close competition here. We actually saw the first place finisher switch places multiple times right up until the closing weekend of the challenge. And for those interested in participating in future challenges, the leaderboard will continue to remain open, and we encourage everyone to submit. So now for the fun part, time to announce the winners for this year's challenge. The grand prize winning team is OP-PRED, composed of researchers from the Opera Research Institute and Waseda University. So they proposed a boundary-aware variant of LaneGCN, which took advantage of new features in Argoverse 2, which posted impressive metrics across the board. We'd like to congratulate the OP-PRED team on their achievement here. We'd also like to award an honorable mention to the runner-up QML team. This is QCraft's 2nd year participating in the challenge after winning first prize last year. So congratulations again to QML. Our second honorable mention goes to the GANet team, composed of researchers from Peking University, Meituan, and Fudan University. So their novel goal area framework extended 2-stage decoding beyond point goals, which they showed to be very effective. Congratulations again to the GANet team. And those are this year's winners. So the next part of this talk will briefly highlight some of the big ideas behind our 3 prize-winning submissions and explore how they compare to the best methods on Argoverse 1. So starting with our grand prize winner, the OP-PRED team extended LaneGCN to incorporate a fusion module that explicitly encodes lane boundary information through graph convolution. The addition of this fusion module was motivated by the desire to capture traffic rule constraints in difficult settings such as lane changes. This model also combines the encoder and fusion modules with a TNT-influenced 2-stage decoder that first regresses a target point before using it as a feature to roll out the full trajectory. The authors also propose a pre-training scheme whereby a target point regression model is trained first, with its weights then being used to start for full model training. So as part of the prize winning entry, the authors also applied several techniques to specifically optimize for the ranking metric. So first off, this model employs a multitask loss formulation with 3 individually weighted components, one for each of target regression, trajectory regression, as well as trajectory confidence. So this allowed the authors to avoid the use of winner takes all loss, which improves training stability. To further improve leaderboard metrics, the authors also employ ensembling to capture predictions from multiple individual submodels, with the final trajectories being obtained through k-means clustering. The runner-up entry from Team QML also shared several similarities. They combined a 2-stage decoder based on point anchors with ensembling using k-means as well. But instead of using a LaneGCN inspired encoder, they used a transformer. And continuing on with that pattern, our second honorable mention also combines a two-stage decoder with a LaneGCN style encoder. But in this case, GANet replaces the TNT-like point goals with goal areas, which makes training more forgiving by relaxing constraints on prediction accuracy. So using a novel GOI crop operator to aggregate contextual information, predicted goal points don't have to be quite as precise, since all elements within a local spatial region can be implicitly captured. So now that we've seen a brief overview of this year's top submissions, let's take a look at what makes motion forecasting on Argoverse 2 harder than the original data set. So looking at the figure on the right, we've plotted the miss rate of 3 different methods on Argoverse 1 versus Argoverse 2. These models have been selected to be representative of the state of the art at different points in time. So Go Home is one of the top Argoverse 1 entries on the leaderboard. BANet is a reduced version of this year's prize-winning entry. And WIMP is an older method from 2020. So when we apply identical methods to these two data sets, we can see a clear increase in difficulty, with each model showing greater than 50% relative increase in miss rate. And we attribute this increase in difficulty to 3 main factors. The first and most important of which is that scenarios in Argoverse 2 are specifically mined to be kinematically and socially interesting, which makes it more difficult for models to resolve in these types of scenarios. In Argoverse 2, models must also be able to handle forecasts for 5 different actor types instead of just 1. And these models must be able to generalize driving behavior to a larger number of cities, which also increases the difficulty. But despite this increase in difficulty, the community has done a remarkable job in closing the performance gap over just 5 short weeks. Looking at initial and final submissions, we can see that multiple teams were able to take advantage of new features such as lane boundaries and headings to improve their relative miss rates by more than 10% over the course of the challenge. Hard mining using actor type was also employed by at least 1 team to significant effect. So yeah, that being said, even with great initial progress, a significant gap to the best metrics posted in Argoverse 1 still exists. And we look forward to seeing continued progress and innovation in future challenges. So to close our discussion on motion forecasting, we'd like to summarize several takeaways from this year's challenge. First off, vector-based methods with attention-based components remain popular and effective. LaneGCN, VectorNet, and transformer-based scene encoders have all proven to be empirically effective, with fairly similar performance across the board. There's no clear best encoder at this time for all situations. All options have proven to be fairly viable. However, 2-stage waypoint and target-driven decoders have become an extremely effective choice for generating multimodal predictions. And with Argoverse 2, we've also seen that new inputs and features will be quickly adopted by the community when provided in an easy-to-consume format. So in this case, lane boundaries have proven to be particularly helpful, forming the basis for one of this year's prize-winning methods. Another common trend we've seen has been the use of multitask loss formulations, with winner-takes-all training being less popular than previous years. Finally, we've seen that ensembling continues to be an effective way to optimize for leaderboard metrics, but this comes with a computational cost that makes real-time inference difficult. So for a more fair comparison, it'd be interesting to measure relative performance given compute constraints. And this is something that we may explore in a future challenge. And that's it. So thank you to everyone for coming to our talk. And thank you to all our participants for making this year's challenges the best yet. And with that, we're happy to take any questions.
Great talk. Thank you very much. Quick question. Have you folks considered using a relative trajectory error for your miss rate instead of a fixed absolute boundary? Because that tends to give too much weight to fast moving targets.
Right. Yeah. So one of the things that became clear to us when we were looking at the per object class breakdown of miss rate was that different actors are probably going to require different thresholds, especially because they have different average velocities, right? Mm-hmm. So if you're a pedestrian, a miss rate of 2 meters could actually be catastrophic versus on a vehicle, it's not quite so bad. Exactly. So in future challenges, we're definitely going to explore dynamic thresholds for miss rate as well as kind of per actor thresholds.
Thank you very much.